you know, these dimensions, and you do all that. But to Brian's point, it's probably for, especially for those of you in DeKalb with the shortened time frame, when you teach them that or get them to ready to do this, if you gave them a blank and it had the lines with blanks, they now know what part, where all the measurements are they need to take, instead of like, if you handed this to a kid, the likelihood that they know they should actually measure this very soft angular change is probably not likely. Like, they'll see that it's there, but they won't compute that that matters, right? They'll just see this, oh, it's a heck of a lot easier if I just did this as a rectangle. Mm-hmm. Right? So, but then you have to decide, in my opinion, right, this is a you decision, which I'm only going to write the curriculum in a way that gives some creative freedom, right? I don't tell you how to tell them to draw it or whatever, because it depends on the software you're using and your comfortability with the software. And what you think your students can digest about the software. If you think your students could draw this wing as a rectangle and then get this little triangular trim and trim it off at the right dimensions, then go for it and teach it to them that way. If you don't think they can, and you say, you know what, it's going to be a lot easier to draw a horizontal line at 33 millimeters or whatever it is, and then go and do a vertical line this amount, and then do a diagonal line this length, and then do all the lengths, and then it just kind of adjusts itself so that it makes the wing, that's fine too. Right? So it just depends on what your comfort level and their comfort level is. So we have all that. So then they're going to model this entire airplane. And then you have the paper one that they're like, okay, I got all these dimensions from my model. And you're like, okay, now you can assemble your model. And now we're going to collect flight data on the model that you have. And they basically repeat the data collection. And it's written in here in the design challenge as they're getting baseline data. This is what this arranged design can do. So they're going to stand at their line, they're going to throw their airplane, and they're going to see how far it went. That's fine, you can leave that. If I keep picking it up and having it, I'll just keep trying to throw it. Keeps me grounded in fact I got to follow it. After they have, say, 5 flights, they have their mean distance traveled, we can now say, great, go back to the data we collected in the data challenge for wing design and take the wing that you felt flew best and design that wing for this plane and see how it compares to the one that was pre-designed. And can we improve the distance travel of this design by adding the data that we collected at the front of that design? Because, right, if you remember the designs we did at first, this one is similar to the elliptical wing. And we said that the elliptical wing was one of the worst, right? So we said it was the delta wing. So can they design a delta wing that fits? Here's the thing. It's got to fit inside of the slot that's built into the fuselage. So that delta wing's only going to be this deep. So now they learn a little bit about proportionality, because if you build a delta wing that has this length just simply translate it to this width, right, it's only going to be like this big. So then what they'll find out is if they design the delta wing to be essentially this, almost the same width as the original, then probably right. And then I throw this.
Did you hear him say what's
Yeah, and you see that how curved, I think, and I'm not wrong, it is because the wing isn't the center. When it's slightly on one side, which has caused it, you have too much lift on one side, which has caused it to
Which
bounce.
is a cool teaching point also, right?
Right,
yes.
Why did it curve to the left?
Yeah. So-
Absolutely.
Once they get it situated, I know the whole thing's kind of wonky here.
Ooh, nice.
Okay?
Nice.
So all of a sudden they now translate what I learned at the beginning to a design modification that creates improved, maybe improved results, right? 7th grade is supposed to be all about invention and innovation. What have we done? We've taken a pre-designed, we innovated it based on data to create a flight improvement, likely, right, in our design.
One thing I try to tell my students, as they go back to their original data, I stress that the designs that we originally tested are intended to inspire or inform your new designs and not necessarily copy it exactly. Oh, the delta wing, well, because of the slot, they have to make some alterations, but they decide to make it elliptical, but it's still going to be elliptical. So I try to get them to take it another step and say, don't copy it straight out. But it can be elliptical S or delta wing S. So it's not a straight copy. But sometimes that's okay too.
What's the logistics, John? So in your classroom, you had like 5 kids. If 3 of the kids are throwing it, right, if they're testing it, what are your 27 or 32 kids?
They're all tester.
So you do the testing all at the same time?
Well, it depends. So what I've seen different scenarios. Sometimes it's a matter of this is a great time for that kind of differentiated instruction time frame, where some kids took longer getting their models to complete and get the right dimensions. So what most teachers that we worked with did was they had this file, right? They knew the results that the students should get. The students went and measured it, and once they measured it, that was their ticket to be able to assemble and do preliminary tests of their model, right? To put it together, make sure that it flew straight, and get the tape together. And for some kids, they did this in the first class period. For some kids, it took them a couple of class periods. So now all of a sudden you have groups that are staggered in where they are in the instruction, and you're able to go around and assist them in that. But once they all got to, all right, sometimes you let them move forward and it's fun for them. Sometimes you let them move forward because it's fun for you. Okay? So sometimes you let them move forward, fun for them. They have everything they need to make it fly really nice, and they have a great experience. Sometimes you let them move forward because it's fun for you. You don't tell them they need a penny. And they get up there and the thing's like, no, this thing doesn't fly. And you're like, well, why wouldn't it fly? See, now that's where you hope that what they did in the beginning with the balls, with the foam gliders, and they put the penny, or it was a penny, right? In the front of the balls of the styrofoam glider, and they then build this. And see, this is where it's like, oh, you had it right. Here's all the dimensions. Oh, all those dimensions are going to make this thing fly right. So they put it all together and they go to throw it and it doesn't fly right. And hopefully their connected brain says, well, wait a sec, when we had the styrofoam gliders, they flew better when we put a penny in the front. Can I put a penny in the front of this? Yeah, sure, here. And they put a penny in the front and all of a sudden the thing flies across the room. They're like, great.
And I totally do that. I have a jar of pennies on my desk.
But don't say anything.
I don't tell them what the jar of pennies is for until they come up and go, can I borrow a penny? It's like, now another thing that we did, what the logistical thing, we did a station rotation where we had like 5 stations that the kids would rotate, and the testing of their flight was like 1. Making the measurements would be 1. We came up with a paper airplane that they would do in Inventor and print out a paper airplane and put their name on it and stuff. I mean, it's just a standard folded plane, but they would do the dotted lines, the cut lines, everything on Inventor, print it out, make a paper airplane, fly it. So we had a terminology station where they're learning all about the terminology of planes and stuff. So they would spend like 2 days or 3 days in each station. So they had time to do this, move through.
So there's a bunch of different.
So that part ends up being a little bit of the incentive to get them through the other.
Correct.
Yeah.
And you might have like, okay, here's a couple of different testing zones. And so I've seen teachers where it's like they have access to their hallway pretty empty. And so they're like, okay, in the front of the classroom is your kind of initial procedural test, right? It's like, get up here, make sure it flies right, make sure it has the weight. And so they're just doing some little stuff here. Then their official test, right, the flight test, where they're actually collecting their baseline data, is a station in the hallway. Right? And now everybody is flying in the same conditions, in the same area. They go out there, when it's their turn, they go out and they can throw their plane and collect their data. And essentially like, okay, you have to do 5 flights in the official test zone. You can collect, right? Here's another opportunity for kind of grade. You can collect that they did 5 flights. And here's the distance traveled for each flight of the baseline flight and the average flight of this baseline design.
So what do you do if one of them goes, oh no, let me do a do-over?
You get 5 throws.
That's 1 and 4 do-overs.
Right. Or it's 4 failures and 1 that works, right? But once they have those 5 flights and the mean distance traveled, they can come in and that's their ticket to now move on to the project and do their modification based on their data challenge results, which is now the Delta Wing. Now this is going to take a little bit of time because, as Brian said, they realize, oh wait, to make a Delta Wing that's this length, it's too narrow, and they go to test it and they're like, wait a second, this doesn't fly all that great, but it's awful small. So then they build a bigger one. Now, I will say that this one's failure is that the fuselage and the tail are made out of this 110 paper, and the wing that was built here is made out of like 50 weight, or the 5mm chipboard, so it's a lot more dense and sturdy, so it actually doesn't have that balance. But
It still flew pretty well.
yeah, it didn't do bad. But if they were the same, if it was made all out of the same material, this one is far superior.
One thing that I did that I had some students ask, because their initial wing testing is with the styrofoam planes, but our design challenge is with
This chipboard.
the chipboard. It's like, they're not the same, so it's not really valid data, because that's different. I have the dimensions and stuff of those styrofoam plane wings in Cricut as well. So you can burn those out. And
Yeah.
then you have, okay, now we have valid data because it's the same material all the way through. So if that's an option, if you want to do that, if you're interested.
It's an option to go
I have
there.
those files.
The other side of that too is the conversation that, in some real testing centers, they test it with more conventional prototype material that is cost effective for testing, right? If you're designing something in 3D and modeling it and producing it on a 3D printer, the initial part for fit and form is cheaper to print them in PLA, because PLA is a cheap material. But when you go to do actual finished production pieces, you might print it in ABS because it's a much stronger supported material, but it's also twice the price. So it's a lot smarter to prototype and test initial in something cheap before you go and purchase and build out of expensive, as long as you understand that for them it's young. In the colleges it'd be different, right? You have to know this material's fit, structure, material science analysis is at this, and the proportional value to the new material would be this, and I accommodate for that, which is kind of what you would be doing by saying the styrofoam was a real cheap way to test some things out, and we found that the Delta Wing was the better design. So now we just translate that to here and we work it out to fit. We're not so concerned by that piece. So, but that's that kind of progression to this, right? But at the same time, when they go to print the plastic, going back to that, right? Oh, I want to print my plane parts. Okay, fine. Print your plane parts, and when they realize it doesn't fly because the mass differential between the paper, the styrofoam, and the 3D printed plastic is so different that when you get more mass, you have to change the dimensions. So, all right, questions at this point? Potty break at this point.
This is one of the favorite activities, the plane, the wing design. For my kids, this is one of the favorite things that they like to do. The building, the doing, the testing, it's active, and the station rotation worked out for us because they're doing an activity, but they're not stuck on it too long, we're able to move along.
Is your rotation on the website, or was it something?
That's something we did individually.
I'd love to see, like that in action.
So yeah, that's what we can talk about, but that was something we came up with because the way I ran our STEM program, it's like, because it was a year long
Yeah.
instead of a semester long, so we had to stretch it out. It was 2 teachers, it was me and Jennifer running it together at the same time, so we had the materials.
Yeah, and that's going to be the difference, right? With the 9 weeks, like, it may take a little tweaking, right? We may not want to like overdo the let's plan for station rotation, because when you get there, you might realize that, oh, you know what, we need to like mass test and move through this because they need to get this done, because you have a week and a half left, and you know they have to get to that next final piece of creating this, and this is going to take them probably a couple of class periods. But the end of this is not just, oh, here's the data that it flew better. The end of this is a presentation as to why, right? This was this design, my data from this told me this based on, and they have to show it, right? Our delta wing had this average travel in the original styrofoam glider. So when our pre-build design had this average distance, and we did these iterations of a delta wing, and they should show, we have, maybe it's a small one, maybe it's a little bigger one, maybe it's even a wider one, and they should have test results that show when we used the little delta wing, and they're holding up the wing by itself, right? It only flew an average of so many. When we used the bigger one, the mean flight was this. But we finished with this design, and the mean distance traveled was this. And then they can say, so here is what our flight looks like. And they throw it, their presentation's over.
So I'm all on board with about presentations. I mean, for STEM, it's a required component.
Yep.
If you're shy, whatever, it's not. So
Yep.
It's so important. But for the constraints of this program, trying to implement it into 9 weeks, have y'all considered, or should we consider asynchronous, where they pre-record their presentations and then just submit them so that we can be watching them or assessing them while they're building something else?
We
Sure.
do that. We've used,
Sure.
I always forget the name of the program, Flipgrid.
Yeah.
And they record the thing.
Yeah.
Now, about the presentation, just I really get on to the kids about that. It's not about, because a lot of kids, well, it didn't work. Our design didn't work.
Yeah.
It flew work. I don't want to do that. It's like, then I have to have a whole conversation about scientists and engineers. It's like, it's not about being right or being successful. It's like your hypothesis. Is your hypothesis right or wrong? Okay, if it was wrong, then you say, yeah, I did all this, my hypothesis was wrong. My designs were wrong, and this is my result. And I even tell them that in a lot of cases, scientists actually try to be wrong. We explain the null hypothesis. So improving what it isn't, so they can say, okay, what's left? It is.
Yep.
And trying to say, I'm not trying to prove this is right. I'm going to prove everything that it can't be that's wrong. To get them feel better about it didn't work. That's okay.
Yeah.
Right.
Can you
Right.
tell me a little bit
I
why
opened
you
up,
think it didn't
right? Our slider project proved to us that it's a good idea, it just can't work in the science classroom. Okay, so to that point, Nathan, the only thing I would, and I think you probably agree from what you had said, is if nothing else, the very last project presentation, which is like, this is my design and this is how I supported it with statistical data along the way, should be done in front of the class. So along the way we do have, right, they're supposed to present about their styrofoam gliders. They're supposed to present about the interior of the airplane. They're supposed to at least show their data files and say, here, right, you don't have to do those in front of the class. You can do those because once they've made that presentation, they're ready to move on and you're ready to move them on. So you can watch those presentations as you're moving them forward anyway. But that last presentation, which should be very data heavy to defend why their design is what it is, should be made up in front of their peers. Because there is something very different about recording it to have it presented versus physically having to stand up there with, 28 other eyes looking at you. Well, actually, I guess that would be like 56 other eyes looking at you. Right? So, all
I
right.
was just going to say, we've had teachers also just fold all of the presentations into one.
Ah,
So they do the presentation from the data challenge, from the fuselage, and from the design challenge. And the presentations still are not very long.
yeah.
Yeah.
But with 35 kids, you're right, it takes a lot of time.
Now, so when we come back from a quick break,
I was gonna say, fucking this thing.
we'll say like 2:45. I want to go back to Brian's statement about like the null hypothesis, because I know at least the DeKalb teachers are very heavy into TSA, and I'm going to give you a little bit of the null hypothesis and kind of gone wrong for TSA. Not in a bad way, just the way kids present. So I want to share that as we move forward with this. So let's take a few minutes. We'll come back at 2:45. So you got about 10 minutes. I guess it's 2:40 now. So 2:50.
Yeah, 6 minutes.
Listen, Doctor Who, who's across the street over here, proved that no bladder takes longer than, I think it's 18 seconds to fully empty. So you don't really need more than 5 minutes.
All the
Well, we gotta get there and all that other stuff.
That's what I'm saying. That's why it's the 5
This is
minutes.
real research.